In this video, we're going to graph each basic variation of a step function, also known as a Heaviside function. This is referred to as u of t. U of t is a mathematical function commonly used to describe a signal or a system turning on at time t equals 0. It will remain on for all t is greater than or equal to 0, and 0 for all t is less than 0. So you can express it as a piecewise function such that it equals 1 for t is greater than or equal to 0, and 0 for t is less than 0. To graph this with t as the x-axis, we can see that it goes up to 1 at time t equals 0. Otherwise, it's 0 for all t is less than 0. To avoid a discontinuity for this vertical portion, we can assume that this is where the actual dot is, and this is where the hole is. But you don't need to worry about that too much. So far, this is a pretty limited function. It can only turn on at one time. However, what if you want the signal to turn on at different times, like t equals -3 on the left, or t equals +5 on the right? Let's write that here. We modify this expression, u of t, to become u of t plus 3 and u of t minus 5, respectively. To graph it, we have t as the x-axis once more. And you can see here that for u of t plus 3 at t equals minus 3, it goes from 0 up to 1. And for u of t minus 5, it still starts from 0, but this time it goes up to 1 at t equals +5. This isn't perfectly to scale, but you get what I mean. If you noticed, these signs are opposite of the off shift on t. Just think about it logically. For u of t plus 3, if t is all the way over here, -5 for instance, if you would plug in -5 here, u of -5 plus 3 would be u of -2. So the function logically is less than 0, so it wouldn't turn on. If t is on this side, +4 for instance, u of t becomes positive. 4 plus 3 is 7, so it can turn on. And for this example, u of t minus 5, for a value over here, t equals 4 for instance, 4 minus 5 is -1, so it's off. However, if you look at t equals 8 on this side, 8 minus 5 is 3, so it's on. This is a pretty simple way to understand if a function turns on. It's not an official way to do it, but that's how I saw it when I learned how to do this initially. Just like any function, you can amplify it. Simply add a coefficient, such as 3 times u of t, and it will now go to 3 instead of 1, like so. This applies to all and every variation of a step function, and to shrink it, you can multiply by a coefficient smaller than 1, such as 0.7, so it can go to 0.7 instead of 1. Now we know the basics of turning on the signal at any time, as well as amplifying it. What about turning it off? Meaning it starts at 1 and then drops to 0. We must use the time reversal property u of -t. The negative sign has to specifically be in front of the t, not the u. And as its piecewise definition, it's 1 for t is less than 0, and 0 for t is greater than or equal to 0. Graphing it, we start at 1 and then go down to 0 at time t equals 0, and then 0 for the rest of infinity. So you're effectively reflecting u of t across the y-axis. What if you want to turn it off at any time? Same as before, we add or subtract by a constant within the u term. For instance, u of -t plus 4. Or u of -t minus 7. You have to be very careful though. Now we turn off at the same sign of the off shift at t. Graphing it once more. We will mark the transition at 4 and mark the transition at -7. Prior to it, it's equal to 1, and then it drops to 0. Same thing goes for here. It's sometimes easier to visualize by factoring out the negative sign, which would make it u of minus on the outside, positive t to distribute it, -4. And for here, u of minus t plus 7. With this variation, you can again assume that the action of flipping will happen at the opposite sign of the offshift, like in our first example set. So now at +7, we go to -7, just like before. To amplify, the same process applies. I'll do it over here. We can multiply constant 8 times u of minus t minus 1. And rewriting that would be 8 times u of minus t plus 1. So we know the transition happens at -1, where it's 8 before and 0 after. We have one concept left. Up to this point, we assumed on implied some value above 0, or the x-axis, for t. Here's an example. This would be on. What if the system required it to be below the x-axis, like here? All you have to do is put a negative sign in front of the u of t, like this, as a coefficient, where its piecewise function is equal to 0 for t is less than 0, and -1 this time for t is greater than or equal to 0. So it looks like this. It's 0 before t equals 0, and it goes down to -1 at t equals 0. To time shift, let's do an example of -u of t plus 3 and -u of t minus 6. We mark the transition at -3, and we mark the transition at +6. So it's at 0 before, and then -1 after. 0 before, and -1 after. Like any other function, we can amplify. -2 u of t, for instance, where the change happens at t equals 0, and it's 0 before, and -2 after. Okay, here's the most complicated variant of these functions. We're going to turn off the function while time reversing it, meaning -u of -t. Its piecewise equals -1 for t is less than 0, and 0 for t is greater than or equal to 0. It'll look something like this. So before t equals 0, it's -1. And after it's 0. We effectively flipped the standard step function on both the x and y axes. Finally, let's time shift it. So we have -u of -t minus 3, which could equal -u of parentheses t plus 3. And for our other example, -u of -t plus 7, which equals -u of parentheses t minus 7. We know here that at time t equals -3, it'll go from -1, since there is no other coefficient for amplification, up to 0 for the rest of t. And in this example, it will happen at +7. It will start at -1 again, and then transition up to 0 for the rest of t. In the case of amplification, we could say -6 times u of minus t plus 3, which equals -6 of u of parentheses t minus 3. It's the same thing. We can again graph it, where it starts all the way down at -6, and then transitions to 0 at time t equals plus 3, where it becomes 0 afterward. That should be everything you need to know about step functions. You'll see these all around engineering courses and topics, so it's pretty important to get used to them early on. I hope this video helped you. If it did, please like and subscribe, and I'll see you in the next one.